How can a charged object reach across empty space and pull something without touching it? There's no contact, but a force appears. We saw this in Coulomb's law. Charges can push and pull over distance. But what's happening in between? This is what electric fields is all about. So before you define it and look at formulas and solve problems, let me teach you the concept. This whole idea of electric fields came from Michael Faraday. And he imagined that a charge sends something out around it. And this something is an electric field, and it exists at every single point in space. If you place a second charge nearby, it feels that field. It doesn't need contact, it just taps into what's already there. Think of it like how Earth has a gravitational field. Even if you're floating above it, you're getting pulled in. It's the same idea with charges, except now it's electric and it can repel or attract. Let me explain to you what a test charge is. To measure the field at a point, we imagine placing a very small positive test charge there. And we assume that the test charge is positive and it just feels the environment without changing it. If a charge Q creates a field and we place a test charge, lowercase q, at a point and it feels some kind of force labeled F, then the electric field at this point is E equals the force divided by the charge. What this means is the electric field is simply force per unit of charge. The units of this value E, so since force is in newtons and charge is in coulombs, then E is in newtons per coulombs. This is on the free cheat sheet in the description. Imagine a positive charge sitting here in the center. From this charge, field lines, I'll write that for you, field lines radiate outward equally in all directions. So if you placed a positive test charge anywhere, immediately, straight away, it would feel a force pushing it away. This means that the field points outward. That's what the test charge tells us, it pushes outward. If the center charge was negative, so negative, then the field would point inward, and all lines would be directed toward the charge. The rule of thumb is that field lines point away from positive charges, and from negative charges they point toward. And the field exists even if no test charge is present. It's generated by the source charge. It's like how even if nothing is falling, the Earth still has a gravitational field. And we can derive the formula from Coulomb's law. Coulomb's law, if you remember, the force from the electric charge is this, which is Coulomb's constant, times the two charges divided by radius squared. Since E is F over Q, F is equal to all of that. So we can plug that in for F. And this is divided by Q. These Q's cancel out, which means that you get K times Q over R squared. This is the field caused by a single point charge. This is also on the free cheat sheet in the description. And this is an alternative version, which is equivalent to this. And it's E equals 1 over 4 pi, this symbol, times Q over R2. We just take it from Coulomb's constant. Both of these are the same thing, and we're going to be using them for problem solving today. How about the direction of the electric field? How do we define that? By definition, the electric field points in the direction of the force on a small positive test charge. So positive, then the field and the force point in the same direction. If it's negative, the field is still the same, but the force that's acting on your charge Q is the opposite. It's time for an example problem. A tiny dust particle in a lab has a mass of 2.2 times 10 to the power of negative 16 kilos, has a charge of negative 3e, which is negative 4.8 times 10 to the power of negative 19 kilo. This little dust particle, you want to try and levitate it. You're trying to suspend it in the air using only an electric field. The question is, what is the minimum electric field strength to keep this particle from falling? This is a force balance problem. You're trying to balance the electric field force with gravity. This electric field, it has to produce an upward force equal to mg, which is gravity. So here's our first equation. F of the electric field equals F of gravity. This is the force equation that we're trying to verify. We're going to see how to make this valid. This is our setup equation. First of all, do you remember the electric field formula? E equals force over charge. We can rearrange for force by multiplying both sides by Q. And we get force of the electric field equals charge times electric field. Next, for gravity, force is given by mg. So, QE is equal to mg. This is our new equation. And what are we looking for? We're looking for the strength of the electric field. So let's isolate E. We get E equals gravity divided by charge, mg over q. Here's where we have to be a little bit clever. The charge is a negative charge. So this here is negative. We want the field to produce an upward force, so the field must point downward. Because if our charge source is negative, meaning the field points toward it, then this negative dust particle will be pushed opposite, which is up. This kind of knowledge will just come with more problem solving and more revision. And when it comes to electric fields, it is an important clarification to make. But in this problem, we only care about magnitude. We will use the absolute value of Q in our calculation, which means we'll just use the positive version. Let's plug everything into this formula. The mass is 2.2 times 10 to the power of negative 16. The gravity is 9.8. And the charge, absolute value, so just 4.8 times 10 to the power of negative 19. This is roughly 4.49 times 10 to the power of 3 newtons per coulomb. This is the value of E. This is the magnitude required for our electric field to suspend this particle in the air. And the direction, it must point downward, so that the force created by the downward field is upward, and it can cancel out gravity. So what is E really? E is the electric field vector. It tells you the force per unit charge at any point in space. And the direction is equal to the force on a positive test charge. The units, newtons per coulombs. If you placed a positive 1 coulomb charge at this location, it would feel a force of 4,500 newtons in the direction of E. In our case, the charge is negative, so it feels a force opposite the field. The field is down, but the force is going up because of our charge sign. The force and the field are not always in the same direction. Here's a second example. Imagine you place a charge Q at positive 4 microcoulombs of charge in space. What is the electric field at the point 0.25 meters to the left of this charge? So here's our Q, and we're looking for the electric field at this point. We're not placing a second charge. We're just asking what field already exists at this point and which direction is it in. The formula for finding charge at a point is KQ over R squared, which is what we derived earlier from Coulomb's law. And it's also on the cheat sheet in the description. It says stuff about the electric field at a certain distance. So let's plug in our values. K is a constant, which if you don't like to remember, it's also in the cheat sheet, 10 to the power of 9 times 9. Our charge value is 4 microcoulombs, which means 4 times 10 to the power of negative 6 normal coulombs. Radius squared is 0.25 squared. The answer for this is 5.76 times 10 to the power of 5 newtons per coulomb. How about the direction? The source charge says positive. That means the field points away from the charge. The field is outward. So if we look at a position to the left of the charge, then the field is pointing left. Direction is left, and this is how much magnitude. Here's some final takeaways or insights. Electric fields exist around any charge. They are force per unit charge, and you can calculate the field at any point using that formula that we used in the previous problem. The direction is always defined using a positive test charge. That's the convention.